So start with the sides. One of the features that's true for all four quadrilaterals with the sides. Well, we notice that in all four, no matter what I do, that opposite sides are always congruent, and we know that opposite sides are parallel, and we know that the diagonals always bisect each other. And we know these are true because we look at the parallelogram and we see these are true statements for a parallelogram. And because rectangles, rhombi, and squares are all specialized parallelograms, we know if it's true for the parallelogram, it's true for all the others as well. So that's what makes it true for all four. But what that also means is there's nothing that's only true about the parallelogram, because if it's true about the parallelogram, I can find that on the rectangle. Opposite sides congruent, true. Diagonals bisecting, true. The anything else we can think of, it's just always true for the others. So then we look at something that's only true about a rectangle. Well, we'd say, oh, maybe it's that the diagonals are congruent to one another, because that's not true about the parallelogram. It's not true about the rhombus, but it is true about the square, because a square is a special type of rectangle. So anything that's true about my rectangle is true about my square as well. In the rhombus, you're like, oh, well, let's see. I have this idea that I have a right triangle inside when my diagonals bisect each other. So I know I could use Pythagorean theorem to find my sides. Oh, but look, the square has that as well, where my four sides are all congruent. Well, square has that too, because a square is a specialized rhombus in a specialized rectangle. So those two things combined. So when we think about, well, what's true only for squares? The square is not that a single item is true, but it's that all four sides are congruent and the diagonals are congruent as well. When you put that and in there, it's the only shape that could happen. So then if we look at angles, we can look at all sorts of relationships in here as well. We know that if we add up the four angles of a quadrilateral, they add up to 360 degrees, so that'll be true for all four triangles. If you look at the angle measures for the parallelogram, what we see is that we end up with the parallel lines that you have these alternate interior angles that are congruent. We can see that we have two sets of congruent triangles. You got this triangle here is congruent to this triangle, and this top triangle congruent to this bottom triangle, except you notice that they're actually rotated 180 degrees. And that's going to be true for the rectangle, the rhombus, the square as well. It's just you start to get more specialized with each of those others. So just like before, there's nothing that's just true about the parallelogram that isn't true about the other three. And just like the others, we know that a rectangle has four 90-degree angles in the corners, and that's also true about the square. What also is unique is that we have that it's made up of two sets of isosceles triangles as well. So if you look at the left and the right triangle and the top and bottom triangle, they're isosceles triangles because we have the two congruent angles marked, and so that helps us be able to see that as well. And we know that the corners, that those are complementary angles. So if we know one angle, we can pretty much find everything because of the isosceles and the complementary angle components. But that's also true about the square. In the rhombus, we have the right triangle, which means if I know one of these angles, then I can figure out the other one because they have to add up to 90 degrees. And we also know that the diagonals create an angle bisector in each of the corners. So if I know one angle, I know the corresponding angle right beside it, and I know its opposite corner as well. So S and P, those angles are congruent, and since it's bisecting, all four of those smaller angles are congruent as well. So we can learn a lot of information. But again, that's also true about the square. And what's unique about the square is that it forms a 45, 45, 90 triangle when I have the diagonals inside. So it's 4 congruent isosceles right triangles on the inside of the square. That's what makes it more unique than the others. So now we can start looking at some of these specific statements that we have here. Opposite sides are parallel. So if I go back here and say, are opposite sides parallel in a parallelogram? Yeah, that's the definition. Is it true in a rectangle? Yeah, opposite sides are parallel. Same in the rhombus, same in the square. So that's true for all 4 shapes. Next one, diagonals form 4 isosceles triangles. So that would mean that 2 sides or 3 sides have to be congruent. Well, here in this one, all 3 of those sides are different, so the parallelogram, I could probably drag it around, but I already have an example shows that I can create a scalene, so that's not true. If I look at my rectangle, congruent side to congruent side, oh, there's isosceles. Here's an isosceles, here's an isosceles, and here's an isosceles. So I have 4 isosceles triangles in the rectangle, and again, I can move it and see this is still true no matter how I change the size or orientation of my rectangle. If I look at my rhombus, well, no, I can already see looking at that triangle right there, that's not an isosceles triangle, so it's not true about the rhombus. But if I look at the square, all my inner diagonals are the same measure, so that no matter what I do, they stay the same. So that's a statement that's true for the square and the rectangle. Diagonals bisect each other. They cut each other in half. So let's look at our diagonal measurements here. That's 2 and 4500ths, 2 and 4500ths, 2 and 5600ths, 2 and 5600ths. That means they have been bisected, and I can change it, the orientation of my parallelogram, and it's still holding true. And if it's true for the parallelogram, it's true for all 4 shapes. So let's look then at perpendicular. Perpendicular means that when they intersect, there's a 90-degree angle. Well, I can see that these 2 angle measurements are not, whereas when you put the angle measurement here on the square and on the rhombus, it forms that 90-degree icon. And I can verify if I go over to the angles, see 90 degrees, and no matter how I drag it, it stays 90 degrees. Whereas I can easily see these are not 90 degrees in the center. So that's true for the rhombus and for the square. Next one down was diagonals are congruent. If I look back at my diagonals, well, 2 and 2/10 and 2 and 2/10 is 4 and 4/10, but the other two, when I sum them, is 5 and 2/10. So they're not congruent. Just looking at that single example, and I can see that's true if I drag it around. If I look at my rectangle, if I add up the 2 smaller pieces, they always create congruent diagonals. So this one's true for the rectangle. For the rhombus, this is kind of like the parallelogram. 1 and 50/100ths plus 1 and 50/100ths is not equal to 1 and 83/100ths plus 1 and 83/100ths. So not true for the rhombus. And then for the square, it's just like the rectangle, so it's true there. So the opposite primary angles are right. So let's go back to our, let's go into our rectangle. And if we see opposite primary angles, that's the big angles like L, N, M, and K. Well, in a parallelogram, if I have 44 and say 29, that is not 90 degrees. So parallelogram, not necessarily true. The rectangle, if I add 39 and 51, that's 90. And if you think about what's the definition of a rectangle, is that it's made up of 4 right angles. So that is true for the rectangle. The rhombus, well, that's 61, 61. That's 122 over 122. So that doesn't have to be true for the rhombus. But the square, if it's true for a rectangle, it's true for a square. We can see 45 plus 45 is 90. So all 4 corners are 90 degrees. So that is a statement true for rectangle and for square. Next one, diagonals bisect primary angles. So that would mean it cuts the primary angle in half. Well, if I look up here, those 2 measurements are not equal. They're not, so it's not bisecting that angle. So in parallelogram, not a true statement. In a rectangle, those measurements are not bisected. So it's not true for the rectangle. Now let's look at the rhombus. Let's see if we can make it a little bit larger here. Well, if I look at these measurements, 27 and 1100ths, 27 and 1100ths, 27 1100ths, 27 1100ths. So it's bisecting that angle, and same for the opposite angles as well. And if it's true for the rhombus, it's true for the square. And you see it's got all 45s that are being bisected. Next one, all sides are congruent. So we go back to our quadrilateral sides. Well, those sides are not congruent. I don't even have to drag it to see that's not always true for a parallelogram. I can see that's not always true for a rectangle. But the rhombus, well, that's the definition of a rhombus, is a parallelogram with 4 congruent sides. That's true for a rhombus. And if it's true for a rhombus, it's true for a square. 4 congruent sides with the 4 right angles makes a square. So these last two, it says find a statement that's true only for rhombi. This cannot be done because anything that's true about the rhombus is also true about the square. That's the definition of being a specialized group within the rhombus. Last one there is a statement true only for squares. We could say that a square is the only quadrilateral. All sides are congruent and all 4 angles are congruent as well. You could say the square is the regular polygon of the quadrilateral family. That would make a unique statement only about the square.